You're floating. The water around you is warm, warmer than you expected, somewhere between a bath that's gone cold and a fever. And it's not clear. It's not that crisp, blue Maldives postcard water you might be imagining. This water has weight to it, density. It pushes back against your skin like something thicker than water should be. Because it is. The smell, if you could smell it, would hit you before anything else. Iron, rot, the thick biological reek of the first forests decomposing into the sea in enormous quantities, releasing tannins and acids that stain the water like cold tea. The Devonian Ocean wasn't just alive, it was fermenting. And underneath you, below the 6 feet of visibility you're working with, the water just continues, down and down. And the thing you need to understand, the thing that matters, is that something down there already knows you're here. That feeling, that specific, wordless certainty that something is below you in dark water, that is not irrational. That is not a quirk of modern anxiety. That is a memory. Thalassophobia, humanity's near-universal fear of deep, open water, didn't arrive from nowhere. It was earned, paid for over hundreds of millions of years by every ancestor of yours that didn't have it and learned too late that they should have. 419 million years ago, something changed in Earth's oceans. The water went from dangerous to comprehensively, inescapably, terminally hostile. And today, we're going back to find out exactly why. Welcome to the Devonian, the age that made you afraid. Before the creatures, and we will get there, I promise you need to understand the world they lived in, because the Devonian wasn't just a different era of Earth's history, it was a different planet. The year is roughly 400 million years ago. If you could look down from orbit, the first thing that would disorient you is the water. There is so much of it. Today, oceans cover approximately 70% of Earth's surface. In the Devonian, that number was closer to 85. Entire continents, North America, Europe, India, simply did not exist as separate landmasses yet. 4 enormous bodies of water dominated the globe. The largest, the Panthalassic Ocean, made the modern Pacific look like a regional body of water. At its widest point, it stretched twice the width of the Pacific. You could sail in any direction for thousands of miles and never once find land. Near the equator sat Euramerica, the fused landmass of what is now Europe and North America, surrounded on all sides by warm, shallow, biologically explosive seas. To the south, the supercontinent Gondwana held together Africa, South America, Antarctica, India, and Australia in a single enormous mass, between them and around them ocean. Warm ocean, stable ocean, the kind of consistent, equable, thermally reliable conditions that evolution absolutely loves, because stable conditions mean long, uninterrupted generations of refinement, of optimization, of getting better at killing things. In every shallow coastal shelf, every warm equatorial basin, every sunlit reef surrounding these continents, evolution was conducting an experiment. The largest, most ambitious, most terrifying experiment it had run since the Cambrian explosion 500 million years before. It was building an apex food chain, and it had 60 million years to perfect it. Let's start with the one you know, Dunkleosteus. This animal is typically introduced as the first sea monster, a title it wears completely honestly, because what Dunkleosteus represented was genuinely unprecedented. Before it, nothing in Earth's oceans had combined this mass, this armor, and this degree of predatory engineering into a single body. It was a placoderm, an armored fish, and it sat at the top of a dynasty of armored fish, the Dunkleosteoids, that effectively owned the Devonian Ocean for tens of millions of years. But the original was on another level entirely. Pinning down its exact size has driven paleontologists to distraction. The armored dermal bone plates covering the entire skull and the front portion of the trunk was essentially indestructible. It fossilized beautifully. The soft-bodied rear half? Gone. Every time. Which means we're reconstructing the full animal from half its skeleton, and estimates range from 4 meters on the conservative end to 10 meters if the largest fragments are to be believed. The working consensus is around 5 meters, roughly 16 feet. About the length of a large great white shark. But here is where length becomes the least relevant measurement. Because of its build armored, heavily reinforced, extraordinarily dense, even a mid-sized Dunkleosteus could exceed 2 tons. That's more than the heaviest great white ever documented. And at that weight, at that build, something human-sized is not a threat. It barely registers as a challenge. You are, in the most clinical possible sense, a snack. And the delivery mechanism for that snack was extraordinary. Dunkleosteus had no teeth in the way we'd recognize them. Instead, the edges of its jaws were formed from massive self-sharpening plates of bone razor-edged, constantly honing themselves against each other with every bite, like natural scissors that never dulled. The force those jaws generated at the fang tips exceeded anything recorded in any living or extinct fish. The kind of force that moved through bone and heavy armor like they were suggestions. We have direct evidence. A specimen of Titanichthys itself, a massive placoderm, was found bearing bite damage attributed specifically to Dunkleosteus. Even within its own weight class, nothing was immune. But the bite force isn't the part that should keep you up at night. It's the speed. Dunkleosteus opened its jaws using what biomechanists call a 4-bar linkage mechanism, the same engineering principle found in industrial pump jacks and heavy machinery. This system allowed the jaw to achieve maximum opening in 20 to 60 milliseconds. 20 milliseconds to go from closed to fully open. And here is what that means in water, because water is the key detail everyone forgets. Sound travels through water at roughly 1,500 meters per second, 4.5 times faster than through air. Every movement, every pressure wave, every acoustic event is amplified and transmitted almost instantaneously through the medium you're both floating in. When those jaws snapped open at that speed, they didn't just open, they created a pressure event, a concussive vacuum, a biomechanical shockwave that propagated outward through the water in every direction. The thud of that jaw mechanism firing would have hit you before you even processed that it had moved. At close range, the pressure differential alone could rupture eardrums, burst blood vessels, cause immediate disorientation, and then before the echo of that shockwave had even finished traveling the suction. That speed of opening created a powerful inward current, pulling water and everything in it toward the open mouth. You wouldn't be swimming away from Dunkleosteus in that moment. The physics wouldn't allow it. You would be moving toward it, and then the bone blades would close. Dunkleosteus was found throughout North America, Europe, and Africa. It hunted shallow coastal waters and open ocean alike. The Dunkleosteus family it spawned included more than 10 species distributed across every major Devonian sea, many of them reaching bull shark size, several of them actively hunting large prey. Eastmanosteus, Westolosteus, different names, same essential promise. One of its relatives, the Heterosteus, found in Europe and Greenland, actually exceeded Dunkleosteus in length, reaching an estimated 6 meters, roughly the size of a small orca. Likely a plankton feeder, likely harmless in intent. But harmless in intent means nothing when something orca-sized materializes from the dark water in front of you. There was no corner of the Devonian Ocean that didn't have something armored, enormous, and hungry in it. And we haven't left the fish yet. Most predators betray themselves. Size creates bow waves. Movement disturbs sediment. Something large enough to be dangerous is usually large enough to announce itself. The Onychondantiforms did not follow this rule. This order of lobe-finned fish was globally distributed throughout the Devonian, every ocean, every depth zone, every reef system. And they were built around one principle. You should not know they are there until it is too late. What made them anatomically unique and uniquely horrifying was their skulls. Where most fish have relatively rigid cranial structures, Onychondantiform skulls were assembled from loosely articulated bones, not fully fused. In some cases, barely connected. This gave them a jaw system with extraordinary kinetic flexibility, closer to how a snake unhooks its skull to swallow prey than anything you'd expect from a fish. This meant 2 things. First, they could strike with explosive whip-crack speed, snapping that flexible skull forward like a released spring, without any risk of fracturing their own bones from the force of it. Second, they could open their mouths wide enough and angle them precisely enough to consume prey far larger than other similarly sized predators could manage. And the teeth. The teeth deserve their own discussion. Throughout the entire mouth, lining the jaws from front to back, were needle-like teeth, dozens of them, fine, sharp, densely packed, but at the very front, something different. Enlarged, curved, tusk-like teeth arranged in whorls, rotating spirals of dentition that were retractable, mobile, actively controllable. Picture a lamprey. That circular mouth, that conveyor belt of inward curving teeth that grip and hold and do not release, now scale it to 13 feet. Now give it a neck that can move independently because unlike most fish, Onichandantiforms had enough cranial flexibility to actually turn and angle their strike. And then give those front teeth the ability to extend, rotate, and thrust independently of the jaw itself. These weren't just teeth, they were weapons the animal could aim. The largest member of the group, Onychodus, appeared in shallow waters, deep waters, reefs, open ocean, cosmopolitan range. Adults reached 4 meters and 160 kilograms, the weight of a female lion. And paleontologists believe it hunted by using its strong pectoral fins to walk silently along reef floors, drifting beneath prey like a slow shadow before the skull snapped forward. A confirmed specimen was found with prey inside it, half the animal's own body length, swallowed completely whole. If being swallowed whole is somehow the preferable outcome, you begin to understand what kind of animal we're discussing. Here is a thing that most people don't appreciate about the Devonian. It wasn't just fish. The Eurypterids, the sea scorpions, were already ancient by the time the Devonian began. They'd been here since the Ordovician, evolving quietly, diversifying slowly. But in the Devonian, something unlocked. What had once been a relatively limited group exploded into over 100 distinct species, occupying every available ecological niche from open ocean to freshwater estuaries. And some of them grew. Jakelopterus. Found in closed coastal bodies of water bays, lagoons, semi-enclosed seas where it held apex predator status without serious competition. Individuals grew to over 2.5 meters. 8 feet of armored, segmented, arthropod body moving through the water toward you. It weighed, by some estimates, more than a fully grown reindeer. And it was fast. Unlike some Eurypterids that used a stinging tail as their primary weapon, Jakelopterus had evolved a powerful swimming tail specifically so it could generate speed, freeing its front appendages for pure offense. Each pincer reached a meter in length. 3 feet of articulated gripping claw, lined with sharp, uneven projections designed to catch, hold, and not release. We know exactly how it killed. A fossil fish was found bearing deep puncture wounds that precisely matched in shape, in spacing, in depth the pincers of Jakelopterus. We don't have to speculate about what it did to prey. We have the evidence pressed into stone. Some Eurypterids carried venomous stingers. Others had telson shaped like serrated blades. Still, others used wide, raking appendages to sweep prey from the water column. And then there was Hibbertopterus, broader and heavier than Jakelopterus, potentially rivaling the mass of a large cow which may not have been purely aquatic. Whether it could operate on land remains scientifically uncertain. Which means the shore was not necessarily safe either. Let's say you've decided. The ocean is done. The rivers are done. You've found high ground, solid earth beneath your feet. You're standing at the edge of the water, watching it from a safe distance. I need to tell you about the Elpistostegalia. This clade of fish, and calling them fish at this stage, is already doing them a kindness. We're in the middle of doing something that had never happened before in the history of animal life on Earth. They were deciding that water wasn't enough. They were learning, generation by generation, to exist on the boundary between the ocean and the land. The most famous among them is Tiktaalik. And there is a persistent, deeply inconvenient misconception about Tiktaalik that needs to be corrected right now, because many people imagine it as something small, a curiosity, a transitional fossil, interesting to scientists, irrelevant to anything with survival instincts. It was 9 feet long. Tiktaalik had gills and scales fish traits. But it also had functional wrists, a neck, lungs, ribs. It could prop itself up on its front fins and hold that position. It could move across mudflats using those fins as primitive limbs, dragging itself forward across the mud with the slow, deliberate movements of something that doesn't need to rush because nothing is chasing it. And here is the detail that matters more than the size, more than the wrists, more than the lungs. Tiktaalik could turn its head. Most fish cannot do this. A fish that perceives something to its side must turn its entire body to face it. Tiktaalik, with that independent, articulated neck, could simply look. It could register your presence at the water's edge, and without moving another muscle, rotate its skull and lock its eyes directly onto you. 2 rows of sharp teeth. A skull that paleontologists consistently describe as crocodilian in its proportions, wide, flat, built for ambush from below the surface. No confirmed predators at adult size. An animal that belonged, technically, to the water, but that was beginning to understand that the definition of its territory was negotiable. Its relative Panderichthys could exceed the length of a standing NFL player. Another relative, Acanthostega, was pushing further onto land with every passing generation. For the first time in Earth's history, the water's worst residents were scouting the border. The line between safe ground and dangerous ground was dissolving. There was no geography left that you could honestly call neutral. The oceans were covered. The shallow coastal waters were covered. The land margin was covered. The rivers had also been covered, and nobody talks about the rivers. Before the Devonian, freshwater systems, rivers, lakes, inland seas were relatively benign, not empty, but not like this. The Devonian changed them completely, and the primary agent of that change was a group of lobe-finned fish called the Tristochopterids. These animals colonized virtually every significant river and lake system during the Devonian. They diversified into dozens of forms. Most were manageable, some were not. The largest Hyneria reached the length of the biggest bull sharks ever documented. Bull sharks, for context, are considered among the most dangerous fish alive. They are the primary species behind fatal attacks on humans in shallow, murky, warm water. They can navigate freshwater. They are aggressive, opportunistic, and built for confined spaces. Now, take that size, put it in a Devonian river, and replace the shark teeth designed to slice with straight, conical, needle-like teeth reaching 5 centimeters each. Twice the length of a bull shark tooth. Not designed to cut, designed to puncture, to grip, to hold in thick, debris-choked, near-zero visibility water that smelled of iron and rot and the tannins of the first forests leaching into every current. Hyneria wasn't hunting in open water, it was hunting in the dark, in the places where the canopy overhead blocked the light and the decomposing forest floor had filled the water with so much organic matter that seeing more than a few feet was impossible. But Hyneria could still find you. These fish developed large, sensitive lateral line canals, pressure-sensing organs along the body that detected movement, displacement, the subtle shift in water pressure made by something walking along a riverbank. You didn't have to be in the water. You had to be near it. And some paleontologists suggest Tristochopterids, with their powerful, weight-bearing fins, were capable of launching themselves partially out of the water onto banks, ambushing anything that thought proximity to the edge rather than submersion in it was the danger. In the Devonian, the concept of a safe distance from water had been abolished. There's one more piece of this picture that most people miss entirely, and it explains something that otherwise doesn't quite make sense. Why were these animals so fast, so metabolically aggressive, so relentlessly active for creatures we'd typically think of as slow-blooded, primitive fish? The answer is in the air. Or rather, what was happening to it. The Devonian was the age of the first forests, the explosion of land plants, the first true trees, the first extensive root systems, the first genuine forest canopies represented something unprecedented in Earth's history. For the first time, photosynthesis was happening on a massive continental scale, and photosynthesis, at scale, does one thing above all else. It produces oxygen. Oxygen levels during the Devonian were climbing toward levels significantly higher than today's 21%. a trend that would peak in the Carboniferous at what some estimates put at 35%. But it was already rising sharply during the late Devonian, and that rising oxygen was pumping into every aquatic ecosystem through gas exchange at the water's surface. Higher dissolved oxygen in water means more aerobically capable animals. More oxygen means more ATP. More ATP means faster muscles, faster metabolism, higher sustained activity levels. These weren't slow, cold-blooded animals moving through the water in the languid, energy-conserving way that most people imagine prehistoric fish. They were running on high-octane fuel. The 4-bar linkage jaw of Dunkleosteus wasn't just mechanically fast, it was driven by musculature operating in a highly oxygenated environment. The explosive strike of Onychodus wasn't just a product of its flexible skull. It was powered by an animal operating at metabolic rates closer to what we'd associate with warm-blooded predators. The Devonian Ocean wasn't just full of monsters. It was full of fast ones. 372 million years ago, it ended. Not quickly, not cleanly. The late Devonian extinction was not a single event, but a series of pulses, volcanic episodes, possible impact events, the ocean chemistry shifting as all those new land plants changed what washed into the sea. Whatever the cause, or combination of causes, the result was categorical. 50% of all genera gone. Every species of Dunkleosteus extinct. Every Onychodontiform gone. Every Tristicopterid wiped from the freshwater systems they had colonized so completely. The sea scorpion diversity that had taken tens of millions of years to build gutted. Rebuilt from a fraction of what remained. The waters of Earth, for the first time since before the Devonian began, were quiet. And this is the part where, if this were a story with a proper ending, the narrator would tell you it was over. The monsters died. The water became safe. And in the eventual fullness of time, something small and tentative crawled out of the sea, stood upright, and inherited a planet that had been cleaned up on its behalf. But here is the thing about extinction. It doesn't erase the blueprint. It just files it away. The Carboniferous came, and with it, arthropods the size of eagles and millipedes the length of cars. The Permian brought new horrors to the deep. The Mesozoic, the age of reptiles, handed the ocean back to predators that made the Dunkleosteoids look like a warm-up act. Mosasaurs, plesiosaurs. Sharks refining themselves generation by generation towards something approaching perfection. Every time the slate was wiped, evolution looked at what remained, considered what had worked before, and started over. Smarter, more efficient, harder to escape. And then there is the coelacanth. The coelacanth is a lobe-finned fish, a direct evolutionary descendant of the same lineage that produced some of the Devonian's most remarkable creatures. For decades, science considered it extinct, another casualty of deep time known only from fossils, a remnant, a memory pressed into stone. Then, in 1938, a fisherman pulled one up alive off the coast of South Africa. Alive, unchanged. As if it had simply been waiting somewhere. The light didn't reach, in the deep water, in the trenches, in the parts of the ocean where human instruments still can't tell us with certainty what's down there. We have mapped more of the surface of Mars than we have mapped the deep ocean floor. The trenches, the Hadal Zone, the places below 6,000 meters where pressure would crush a submarine remain, in large part, unexplored. We have footage of perhaps a fraction of a percent of what lives there. The coelacanth was hiding for 66 million years, and we had no idea. So when you're floating in open water, when that old, wordless certainty arrives that something is below you, that the dark beneath your feet is not empty, that something down there already knows you're there, maybe that instinct isn't irrational after all. Maybe it's just remembering. Thanks for watching. And if you weren't afraid of the water before, you're welcome.